on adding numbers in scientific notation. And we talked about how you could keep the numbers in standard form, and you can, okay? But that would be more of a way to check yourself. Okay? The learning target for 8th grade is that you can do these operations with the numbers in scientific notation. Okay, so it's important as you approach an exam or a quiz that you're at least attempting this. Now, I am a huge believer in showing the numbers in standard form so that you know if you're on the right track. If you make a mistake, it's going to be somewhat obvious when the number's in scientific notation. If you already know what the answer would be in standard form. Okay, so today we're going to talk about subtracting. Subtracting numbers in scientific notation instead of adding like we did on Friday. So first, we can convert this number, this 6,300,000,000, into scientific notation. How would we write that number in scientific notation? What do we need to do to represent this number appropriately? My first number, good, in scientific notation must be between 1 and 10. So what number can we use here that's a factor of 6,300,000,000?
6.3.
Yeah, 6.3. Good. And I'm going to multiply that by a power of 10. How do I determine the power of 10 that I'm going to multiply 6.3 by? I'm going to utilize place value. If I am going to multiply the number 6.3 by a power of 10 until I get 6,300,000,000, how many times will I multiply by 10? 9 times. Good. So 10 to the 9th. So on Friday when we were adding, we got to this point. We started to realize that our exponents matter. Why do exponents matter when we're adding or subtracting numbers in scientific notation? What do the exponents represent? Place value. And you learned, when you learned how to add and subtract way back in the day, your teachers always said, line them up, right? And they talked about place value because we can't just add all different place values together. The position matters. And that's where the exponents come into play. So an option that you have would be to create a table such as this. Now, you don't necessarily need a big drawn-out table, but let's take a look at what's happening. On the right side, we have 6.3 times 10 to the 9th. What happens as the exponent goes down from this cell here? As the exponents decrease, what do I notice? What do you notice?
Dot.
Yeah, the base number, that first number, is doing what? It's increasing. If I'm going from 10 to the 12th to 10 to the 11th, what am I doing to that power of 10? What do you mean? By reducing that 12 to an 11, what did I do? What operation was it? If I went from a power of 12 to a power of 10. Well, I took away one of the powers of 10. What operation is that? Say it again. Yeah, if I divided by a power of 10, what do you notice about this first number? It multiplied by 10. As I divided my right side by 10, my left side multiplied by 10. What do you know about each number here? This number, this number, this number, this number. They're the same number. Yeah, I'm just rewriting it in a different way. Right? There's a reason why I might do that. Right? Take a look at the cells on the left side, the 5.1 times 10 to the 12th. If I need to show this with a different exponent, as my exponent decreases by values of 10, or powers of 10 I should say, my first number here is increasing by powers of 10. Now some of you might look at that as I have the arrows and think of slope and tables. It's a little different because these are all the same number. We're just rewriting them in a different way. And for those of you that need to see it visually, we can do 5.1. That's a bad 5.1, so I'll try it again. Times 10 to the 12th. 512. So when I first represent that number in scientific notation, I have 5.1, and I'm multiplying it by 10 to the 12th. But let's just say I wanted to represent that number as 10 to the 11th. What would my first number need to be? What do I have to do with this? If I'm now only representing my power of 10 as 10 to the 11th, what do I have to do with that 10? Yeah, I'm going to multiply it by the 5.1, so that would be 51. Now let's say instead of 10 to the 11th, I actually wanted to show this number as 10 to the 10. These are going to be my power of 10. What would I need to do with both of these 10s? I would need to multiply both of them by the 5.1, and that's where I would get the 510. So if at any point in time you were struggling to see why that original number is changing or why the exponent is changing, I encourage you to break out the number and actually show the movement. You can see where that power of 10 is coming from. Some of you might just be able to fill in the pattern, right? If you notice that every time I decrease by a power of 10, this number is increasing by a power of 10, that might be enough. Now some of you might look at this and say, why does this matter? We talked on Friday about why this matters, and you kind of reiterated it a few minutes ago. You said the place value matters. So now at this point, any pair of numbers from this table can be used to successfully subtract these two numbers in scientific notation. My question for you would be, which numbers would you use? If you had to finish, now you are going to finish this problem. You're going to do the subtraction and actually subtract 5.1 times 10 to the 12th minus 6.3 times 10 to the 9th. But before you do that, take a look here at the table that we have filled in. Okay? Which power of 10 are you going to use?
10 to the 10th power.
10 to the 10th. Jordan's going to use this one. Why?
Well, it just like, it's easier to me. Like 10 times. Like,
Okay.
And then like 5, 10, and then 6.8. It's just easier.
Okay, which part? Are we looking, if you're talking about subtracting, are you looking at the 10 to the 10th, or are you focusing on these numbers when you think about what you want to subtract?
Yeah.
Okay, what is it about 510 minus 0.63 that might be a little bit easier than, say, 5.1 minus 0.0063?
It's like a decimal subtracting more decimal.
Okay,
That
Yeah.
one's like a whole number then, like, so you don't have 2 decimals to do it. So.
yeah, absolutely. If you can't hear what Jordan's saying, all of these answers, you're going to get the same answer, right? They all have the same value because every number here on the left side is the same number, and all the numbers here on the right are the same number. They're just represented differently. When you start to look at subtraction, think about what problems may come up. You might be a little pickier when it comes to subtracting numbers in scientific notation than adding. What are some common problems that you might run into when you subtract numbers? Say it again. Okay, aligning the place value. Now, right now, with these numbers in scientific notation, less issues maybe with place value. So here's what we're going to do. I want you to finish this problem. You can work together as you go through this, but we're going to compare our answers because there's a chance that not everyone gets it completely correct. And if you don't, we're going to use that as a talking point to figure out why you might be a little bit more selective to subtract using one of the numbers versus the other. So take a couple minutes here and finish the problem. Your eyes should be open, your pencil should be in your hands, and we should be finishing this problem here, and you can work with the people that you're sitting around and have a conversation about which numbers you want to use.
Yes.
scientific notation.
5 tenths times 10 to the 10th. Subtract 6. 0.6.
Does anyone want to share which numbers they use to subtract? I know Jordan mentioned she was going to use the 510 times 10 to the 10 minus 0.63 times 10 to the 10th. Did everyone use that number? Did anyone use something different? Okay, we'll use that one. What do we get if we subtract 510 minus 0.63? 509.37. And that was times 10 to the 10th. Am I done here? No, not yet. Now, if you were at this level, that'd be a 3. You did it right. But still, we can represent this number in proper scientific notation. How would I do that? Or what is the first number when this is in scientific notation? 5.0937. And what would my exponent be? 10 to the 12th. Yep, these two place values, I would have to shift them over here to the exponent of 12. Did everyone get that?
Yeah.
Did anyone not get that?
Yeah.
Okay. Now, but when you look at this, some students earlier in the day struggled a little bit. Students earlier used all of them, and they tried it. And what they found, from earlier classes, more students had problems with this one. The borrowing got to be a little problematic. Okay? Whereas the students who used either the 10 to the 10th or the 10 to the 9th, they didn't really have an issue so much with borrowing. Especially like 5,100 minus 6.3, you could do that in your head. Right, 5,100, if I take 6 away, I have 5,094. And then if I have 5,094 and I take away 0.3, I have 5,093.7. Or you could do that, think about money, right? Students who are using these numbers were thinking more along the lines of money. Maybe less likely to make a mistake. Adding is a little different because most of us feel pretty comfortable adding no matter what we add together. Subtraction, when you start to talk about borrowing and things like that, it's been a while since you've done some of those things. Those skills could get a little rusty. Certain numbers may be a little bit more preferred. So now let's take this number and show it both ways. I'm actually going to pause the video here so that you can take your time and not feel rushed. We are going to solve this in standard